Interference of light. Light is an example of transverse wave. In a light wave, the electric field, magnetic field, and the direction of wave propagation are mutually perpendicular to each other. Both diffraction and interference of light are evidence for wave nature of light. An interference of light can be examined in two experiments. The first one is Young's double-slit experiment. The second one is pink diffraction grating. Interference of light by using Young's double-slit experiment. When a monochromatic light passes through a double slit, interference patterns is observed on the screen. The results show that the separations between successive bright fringes, delta y, is constant value, with delta y equal to d lambda over A, where d is the slit to screen distance. Lambda is the wavelength of the monochromatic light. If it is red light, then lambda is the wavelength of red light. A is the slit separation. Notice that the conditions for Young's double-slit experiment is that both the light wave passing through the two slits must be of the same frequency. Another formula for Young's double-slit experiment is y equal to md lambda over A, where y is the distance of the bright fringe of the order m from the central maximum. If m is equal to 2, that is the second order maximum, then y2 equal to 2d lambda over A. Question number 1. The fringe separations on the screen, delta y, is given by d lambda over A. In A, if monochromatic light source of longer wavelength is used, that is, the wavelength increases. Therefore, the fringe separations will also increase. B. If we use double slit with a greater slit separation, that means A increases. In this case, the fringe separation will decrease. Part C. If we use double slit with a larger slit width, that means only the slit width increases, but the slit separation A still unchanged. In this case, the fringe separations will not change. Question number 2. Delta y equal to d lambda over A. Therefore, lambda equal to A times delta y over d, which is equal to A is 0.2 times 10 to the power negative 3 meter. Delta y is equal to 2 times 10 to the power negative 3 meter. D is equal to 0.8 meter. Therefore, the wavelength of the monochromatic light is 5 times 10 to the power negative 7 meter, or equal to 500 nanometer. Notice that 1 nanometer equal to 10 to the power negative 9 meter. Interference of light can also be studied by using diffraction grating. If a grating has n lines per cm, then the slit separation A will be equal to 1 over n cm. For example, if n is 1000, then A would be equal to 10 to the power negative 3 cm. When a monochromatic light of wavelength lambda incidence perpendicular to the grating, an interference pattern will be shown on the screen. The central maximum is m equal to 0. The first order maximum, m equal to 1. The second order maximum is m equal to 2. And we have an equation a sine theta equal to m lambda, where a is slit separation, theta is the diffracted angle. In the diagram, the angle between this line and this line is the second order diffracted angle. And the angle between this line and this line is the first order diffracted angle. M is the order of maximum. Lambda is the wavelength of light used. Notice that when white light is used instead of monochromatic light, a spectrum will be observed. Question number 3. From the equation a sine theta equal to m lambda, sine theta equal to m lambda over a. For the first order maximum, we have sine theta 1 equal to lambda over a, because m equal to 1. Since red light has the longest wavelength, and for the grating with 400 lines per mm, the slit separation A would be the smallest. Therefore, part C would get the largest value of sine theta 1. Implied, part C will get the greatest value for theta 1. Hence, theta would be the highest because theta equal to 2 theta 1. Therefore, we should get the answer C. Question number 4. The equations for interference patterns is a sine theta equal to m lambda. For red light, we have a sine theta red equal to m for the red, lambda for the red light. And for the violet light, we have a sine theta v for violet equal to m for violet, lambda of violet light. Since the diffracted red light coincides with the diffracted violet light, that means theta r and theta v are the same. Hence, sine theta r and sine theta v are the same. which implies that mr lambda r equal to mv lambda v. Therefore, we have mr over mv equal to lambda v over lambda r, which is equal to 438 over 657. Therefore, mr over mv is approximately equal to 2 over 3 by simplifying this one. Therefore, the respective orders of the deflected red light and violet light will be, the order for red light will be 2, m equal to 2, and the order for the violet light would be 3, that is m equal to 3. mr is 2 and mv is 3. That is, the second order maximum for the red light coincide with the third order maximum for the violet light. Question number 5. The equations for interference patterns on a grating is a sine theta equal to m lambda. We have 5 theta equal to m lambda over a. Since sine theta must be smaller than 1, therefore the order of maximum is smaller than a over lambda, which is equal to 1 over 5000 cm over 650 times 10 to the power negative 7 cm, which is equal to 3.1. Therefore, m smaller than 3.1. Since m is an integral number, that is, it is an integer, therefore the largest values for m is equal to 3 only. Since interference patterns form on both sides of the 0th order, therefore we have m equal to 3 on both sides. As a result, they are altogether 2m plus 1 orders of maximum, which is 2 times 3 plus 1 equal to 7 order of maximum.